Kathy is going to come up and draw the structure, the complete structure, and then I'm going to have Sam come up and give the name. Nope. Beautiful. Yours may not look exactly like this. As walking around, I saw a lot of people do correct structures. But the important thing is that those C2H5 groups, of which there are two coming off of a carbon, here's one of them, here's the other one. Then we have the CH, CH3, CH, CH3, 2. Okay? So it's all there. It's not necessarily the way I would have written that condensed structural formula, but it works. But then once you have the structure drawn out, you need to ignore the way the condensed structural formula put things together. You need to then wipe your mind of all of that and just look for the longest carbon chain. Okay? Once you've found the longest carbon chain, you might want to consider like taking a colored pencil and highlighting it so that you remember where your longest carbon chain is, and then circling the things that are coming off of your longest carbon chain. And then using that to name the structure. Okay, so this is a hexane because the longest carbon chain is 6 carbons. It looks like 3 when it was written out here, like here's 1, 2, 3 with stuff coming off of it, but we're gonna add one of these and one of these. One of the CH3s and one of the C2H5s on the end are gonna be part of the full longest chain. So we can draw it, there's a couple different ways you can draw it. I'm gonna draw it like this. Okay, so there's my 1, 2, 3, 4, 5, 6 carbon chain. Okay, and then I'm going to go ahead and draw circles around all the things that are not hydrogens that are connected to that chain. Okay, so I've got a methyl group here, I've got a methyl group here, and I've got an ethyl group, 2 carbons, there. Okay. So your temptation looking at this is to say you have 2 ethyl groups, but you don't. You have 1 ethyl group coming off of a chain that included the other those other 2 carbons. Okay? You're not going to have anything this complicated to do on the test. Okay? I just wanted to make you struggle with this and then come back and see how it comes together. So now that we have our longest carbon chain, we know it's a hexane. We've got an ethyl group and 2 methyl groups. What I didn't tell you before is that when we are naming these things, if you have more than one type of group coming off of your carbon chain, you go in alphabetical order. So the ethyl comes first because E comes before M. Okay. Yes. Yes. Okay. So now we got to think about, when we're naming, we got to think about our, we got to number our carbons and make sure that we have the smallest numbers. So I could number from here. I could go 1, 2, 3, 4, 5, 6. If I do that, then I've got my ethyl group coming off of 3 and my methyl groups coming off of 4 and 5. If instead I number it 1, 2, 3, 4, 5, 6, now I have my methyl groups coming off of 2 and 3 and my ethyl group coming off of 4. 2, 3, and 4 is better than 3, 4, and 5. We want to make the numbers as small as possible. So we're going to go with the orange numbering. So we've got our methyl groups are coming off of carbon 2 and carbon 3, and our ethyl group is coming off of carbon 4. So 4 ethyl, and then 2, 3 dimethyl hexane. And I saw a lot of folks doing great stuff here that maybe didn't quite get to this or took a little extra fiddling to get to this. But you were thinking along the right lines with trying to name the constituents that are coming off of the main chain. So again, this is more complicated than anything you'll see on a test. Okay. Until you get to college and take organic chemistry. If anybody's pre-med, good luck. No, we'll get you prepped for that. Okay, so another thing I want to point out here is that that was really hard for Kathy to draw, because all those hydrogens coming out every which way, we've got all these branches, which way to put the branch, how to try to make it as compact as possible, as neat as possible, and she still had to cram some hydrogens in over here, okay? And that is not her fault. That is just the way the cookie crumbles when you have this kind of complicated molecule, which is why we don't hardly ever draw full structures. Nobody draws full structures once they get past the beginner stages, because we can get exactly the same information with a much simpler approach, okay? We are going to talk about that today. Before I get to that, though, I just wanted to go back and review what we ended up on Thursday, which was our alkanes. So our halogens getting added to alkanes. And we did, here, let me go back, actually. We did this first one where we found our carbon chain, and I was lazy and didn't write the hydrogens here. We had a 4-carbon chain with a chlorine on one end, and we talked about how we would always number it so that the halogen is the lowest number, just like everything else. And then we're gonna just go from there. So this would be 1 chlorobutane, as opposed to having the chlorine coming off here, which would be 2 chlorobutane. So it's the same approach that you're taking to the methyl groups and ethyl groups, et cetera. It's just you're doing a single halogen that's taking the place of the hydrogen instead of a whole longer group. Okay. So when we ended, I told you that this is one of the very few situations where you're actually going to see a capital I that is iodine in a covalent compound. Usually I tell you to assume that that's a lowercase l, but clearly there's no HL element, and so that is going to in fact be an iodine on that carbon. So just to quickly go through that, we would have our methyl group over here, or our CH3 over here, connected to a carbon, which would have 1 hydrogen and 1 iodine, and then connected to another carbon with 3 hydrogens. Okay? So all we've done is replaced a hydrogen with an iodine in the middle. And that's a pretty classic kind of organic reaction trying to either replace hydrogens or replace other things with hydrogens in order to make different types of molecules. So, what would the name of this substance be? And notice that if we had a double bond, when we had propene, we didn't have to specify because there was only one way there it could go. We could have a double bond and then a single bond if it was just the one double bond. But here with the iodine, we do have to specify if it's on carbon 1 or carbon 2. Okay. All right. So you have everything you need to complete this packet. It's due on Friday. Okay. I will post the, and I've already have slides from last week up, so the last 2 lectures are up, videos and slides. I will post an updated slide show with these slides tonight and put up a video from today's lecture, so you can always go back and look. I will also publish today the answer key for this packet. So could you get a 10-point completion by just copying everything off of the answer key? Yeah, of course you could, and I would never know. I encourage you to try it yourself and then use the answer key to check where you might have gone wrong. And if you have any questions, let me know. Okay. All right. So I want to go back to that problem Kathy was having with how do I fit in all this freaking hydrogens and all these corners, and it's so annoying. And I want to take us back to this slide that we looked at when I first started telling you about the alkenes. And I didn't draw any attention to this thing down here, but this is what we are going to be talking about right now, because this is also a way to show the structure of those compounds. And as you can see, it's a lot easier and smaller and faster to draw than the full structural formula. Okay? So what is going on with these lines? This is called the skeletal structure. The skeletal structure, has a zigzag for single and double bonds between carbons. Every corner and every end is a carbon. Okay? And we are assuming the hydrogens. The hydrogens are assumed. So if you don't see anything that says that there's anything other than hydrogens attached to this carbon, then it's just hydrogens. Anything else will be shown directly on the structure. So this is, what is this? What's the name of this? What's that? Butane. Yeah, this is butane. This is also butane. Okay? This is actually a sort of hybrid condensed structural formula where they wrap the hydrogens in with the carbon that they're attached to. But here we don't even have them written in at all. And every bend in the structure is a carbon, and every end. So every bend and every end. And then there's more to it than that when we get into triple bonds, which I'll tell you about in a second. So for this structure here, this isn't in your packet or anything. This is just something I pulled off online. Each one of these corners is a carbon, and each one of these ends is a carbon. Okay? And we're assuming that everything that's not a bond to another carbon is a bond to a hydrogen. There's no double or triple bonds in here. So this carbon is going to have 3 hydrogens. All the end ones are going to be CH3s. And my hand is already getting tired, which is why organic chemists use this structural approach. Now, these middle carbons, do they have any hydrogens? And if so, how many? They each have 1. Okay. What would be the name of this compound? First of all, what's the longest carbon chain? How many carbons? 4, yep. Okay, so it's going to be a butane. And what are we going to add to that? Amanda, you look like you're ready to say something. I just can't quite hear you. You're not sure? Okay. Yeah. Close, but it's not going to be 1. Yeah. So we've got 2, 3, and then we've got methylbutane. What are we missing? Dimethyl butane. It's a little bit redundant, but you have to include it. Okay? So this is much easier to draw. Oh, that's a blank slide. Okay, so now we have 4 different ways of showing organic compounds, okay? We've got our molecular formula, and actually we'll have even more when we start talking about empirical formulas. That'll come after this unit. Molecular formula. We've got the Lewis structure, or the full structure. We've got the condensed structure written out, and we've got our skeletal structure. Same, all 4 of these things are showing us the same molecule, which is called what? What is this molecule? Someone besides Patrick and Sam. Propane. This is propane. 3 carbons. Prop. Okay. I already did that. Okay. So single and double bonds. You do show the double bond, just as if it's a double bond. Okay. And you're going to do this sort of zigzag approach here for the carbons. And this will make more sense tomorrow when we do some modeling. When you have triple bonds, though, that is always going to be a linear format because each of these carbons has only 2 electron domains, 1 single bond and 1 triple bond. So that's always going to be linear. So you have to make sure that your triple bonds are linear in your skeletal structure, but single and double bonds are going to be at angles. Okay. All right, so the last thing I want you to do with that packet, there are 5 sections. For each section, I want you to pick at least 1 molecule. You don't have to do more than 1, but if you want to, you can. And draw the skeletal structure for that molecule. Okay? And I'm going to, again, I'm going to ask you to turn that in on Friday, including the skeletal structures. Okay? And I'm just going to leave you with one more thing, which is something that we cover more in HL because it matters for stereochemistry, but if you have not before seen, there's one more structural thing that we often use in organic, which is the 3-dimensional structure, which is how we take something that's 2-dimensional. We know that this methane molecule is not a flat cross. It is a tetrahedron. But how do we show that on the page? We use this dashed wedge structure where the wedge is coming out of the screen and the dash is going into the screen or the paper, and the other 2 are in the plane of the page. So it's a way of showing, like if I had 2 chlorines on here, or 3 chlorines or something like that. It's not as big of a deal for something like methane, but when you start getting into compounds that have multiple functional groups on them or with double bonds, then it becomes important to show which side of the molecule different things are on. Not for our purposes, you don't have to worry about it, but you should be familiar with this. You should be able to recognize this. And you don't have to draw it. I don't think there's I have yet to see a question that asks you to draw this, or that, I don't think I've even seen questions that include it as like part of the information they give you. But just in case, it's something that you should be aware of. So tomorrow, we're going to play with models. You might want to bring your Chromebooks charged, because if we have time after we play with the model kits, I might demo some stuff on molecular modeling online, which could be useful for an IA topic if you like organic chemistry and want to do something that does not involve beating your head against the wall, making up solutions, and desperately trying to filter blueberry juice or sonicate albumin in order to make a standard curve. Databases are a lot cleaner. Doesn't mean they're easier. They're just cleaner. Okay. All right, guys. Thank you.